Cellular automata are a very simple way of modelling a range of different complex systems. They really epitomise the idea that simple interactions can produce very complicated patterns. What a cellular automata is basically an array of cells. In a 1D it will just be a line of cells, in 2 dimensions it will be a square of cells, and so on. And what happens on each time step of the cellular automata, we update these cells using a rule by which it interacts with the neighbouring cells all around it. Over time we run it over and over again and we see how the pattern produced by the cellular automata evolves. Now for the most basic cellular automata, which are one-dimensional elementary cellular automata they're called, in these we just look at the 3 cells above to determine what happens in the cell underneath. So in the picture in the middle of this slide, you can see if we have 3 black cells, the cell underneath goes white. If we have 2 blacks and a white, it goes white. Black, white, black goes to white. Black, white, white goes to black, and so on, all the way down to white, white, white goes to white. Now, these rules can be easily stated in binary form. A 1 represents a white, and a 0 represents a black. So in binary, this rule will be 1, 1, 1, 0, 0, 0, 0, 1. We can give these rules numbers, and all we have to do that is convert the binary number into a decimal number. And we just do it as follows, that we'll have 1 plus 2 plus 4 plus 128 is 135. So this rule is rule 135. 256 possible rules, ranging from 0 up to 255.
So to illustrate how the cellular automata works, I'm going to use one of the simulators you can find on the internet. This one's in NetLogo. And what I'm going to do is start with a single white cell up here and apply the cellular automata rule repeatedly through time. Now over here we have the different rules that we can apply, and I'm going to look at rule 254. 254 is quite a simple rule. It says if you've got 3 black cells, they become black, but any other combination of cells go to white. So black, black, white goes to white, black, white, white goes to white, and so on. White, white, white goes to white. Now if I just set up a single white cell at the start, and I do go, then you'll see that this white cell spreads out. And that's because if I look at my rules, every combination apart from black, black, black becomes white. So the single cell just expands out as a triangle which covers the entire area. If I continue this pattern, taking all of these white cells and putting them back up at the top, and go again, then I just continue to have a blank white page. I'm going to look at a few different rules and see which type of patterns come out. It's hardly surprising that rule says that paint everything white makes white things. So if I switch off this one here, show rules, now I'm looking at rule 250. See, now I've got a black here, but also if you've got black, white, black, then it becomes black. Set up a single cell, go, and now I get this alternating checkerboard pattern. The checkerboard pattern comes about because when you have this black, white, black, it makes black, and white, black, white makes white, and you get this alternating checkerboard pattern. Set it up again, go. We can also set up with random starting conditions, and now we actually get a different pattern. Set up again random, run it, and then eventually everything becomes white. Let's try another rule. I'll go to rule 180. Show the rules here. Now we've got a reasonable balance between black and white. Again, when everything's black it goes to black, when everything's white it goes to white, but in between some of the combinations go to white and some of them go to black. Set up a single cell and go. Now we just get a line shooting off into a particular direction. If we set up random, we get lots of lines moving off to the right. So here we have a repeating periodic pattern that arises. Wherever the initial point is, you get a line moving off, and it just repeats in this pattern forever. But there are some much more interesting rules. One of the classic is Rule 90. Rule 90 is related to mod 2 arithmetic. So if we look at the left and right hand cells here, black, black here, if both of these are black or both of these are white, then we go to black. But if one is black and one is white, then we go to white. So here we have the left hand black, left hand white, we go to white. Here, black, white, white. But here both of them are black, so we go to black. But if both are white, then we go to black as well. So this is modular. If we add up 0, 0, then take mod 2 of it, we get 0, so we go back to black. But if we add up 0, 1 here, and we take mod 2 of it, we get 1, and we go to white. So I'll set up a single cell and go. And this produces the following pattern. This is a really nice pattern, and it's an example of a self-similar pattern. So if you look at each of these triangles and cut them out, you see a pattern within the pattern which is the same. We're going to come back to this pattern when we look at box counting dimension and fractal shapes. This is an example of a fractal. So what we start to see now is that just that simple mod 2 rule produces quite a complicated self-similar fractal-like pattern. And there's quite a few rules that do things like this. If we take rule 150, for example, and show the rules, set up with a single shape, go, you also start to see fractal self-similar-like patterns. These aren't particularly dependent on having a single cell to start with. If I set up random and go, I still get those types of self-similar patterns, a bit more compact, but you can still see the same sort of patterns coming out. And it's not just fractals which can be produced by cellular automata. If I take rule 30, set up with a single cell, and go, we start to see, again, triangles, but also some more complicated shapes down here. So there's a degree of complexity which doesn't really simplify to just being a self-similar fractal, with both these line patterns, these triangle patterns, a whole variety of different patterns you see. We can keep this going. We see triangles of different sizes, lines of different sizes, set up with a random and go. And again, you see this complicated, complex mixture of patterns. The same happens for a range of different rules. If I take 110, take 110, set up with a single, go, and we get a sort of left-handed version of 30. Triangles of different sizes, set up with random. Again, we get this left-hand moving thing, but we get very pretty, complicated patterns. It's just easy, you either put in the rule number or use the on-off switch to switch between different rule types. You can show the rules and then set up with a single and go and see the type of pattern that comes up. Set up with random, with different densities. Play around with the different rules and see what type of patterns you get.
So now you should try playing around with the elementary cellular automata yourself. Try a few different rules, see what patterns come out, and just enjoy playing around with the different rules involved. So how do we understand the things that come out of a cellular automata? Well, we can really just start with some empirical observations. One empirical observation, one observation we find by running the cellular automata, is that they produce different types of patterns. And there isn't really a rigorous way known to classify the patterns, but we can classify them in rough groups. So class 1, and that's what we saw with rule 254, is all the cells converge to a black or white set. And there's quite a few rules which produce that kind of output. Class 2, we have periodic patterns, and these repeat the same pattern over and over again like a loop. That's really the checkerboard patterns that we saw. Class 3, they produce chaotic and pseudo-random patterns. And so we saw that with rules 110, for example, and rule 30. But you could also think of those rules 110 and 30 as producing complex local structures. I pointed a few times to the lines and the triangles that were produced by these rules. So it's not clear if rule 30 or 110 fall into one of these different things. Sometimes they produce chaotic patterns, sometimes they produce things that look like they have some kind of clear structure. In fact, I feel that this classification, which is kind of the standard classification of cellular automata, it gives a bit of a feeling as there's three types where we roughly understand what's going on. They're stable, they're periodic, and they're random. And then there's one sort of class 4 type which we don't really understand what's going on. We can make our cellular automata more complicated. We can run for longer interaction ranges. We can have 5 neighbours instead of 3. We can work in 2 or more dimensions, and we could have a hexagonal grid instead of a square grid. So there's lots of different ways we can do it. The other cellular automata I want to show you is the game of life. This is maybe the most classic cellular automata. The game of life somehow captures a few properties of life on a 2-dimensional grid. If you look at your 8 neighbours all around, and if 2 of them are alive, if less than 2 of them are alive, then the cell dies. If there are more than 3 alive, the cell dies. What happens when we have exactly 2 or 3? Well, if we have exactly 2 alive neighbours, we say the cell just remains exactly as it was before. If there's exactly 3 alive neighbours, then the cell becomes alive itself. So in the top left-hand example, we have a cell which has 4 black around it and it goes to white. But just below it there's an example with 2 black above it and 1 black in the bottom right-hand corner, and that goes to black.
So again, like all cellular automatas, the best way to get an initial understanding of them is really to look at them and see what they do. So I've set up here the game of life on a 2-dimensional lattice, and all of the black cells you can think of as the living cells, and the white ones are the dead ones. And I'll just go one step to start off with the rules. And what's happening on every cell of the lattice, I'm applying this same cellular automata rule. And go once, you can see it changes structure a bit. Go again. Now a few of the black cells are dying out. Go one more time. It's still dying out. Now you can see there's some groups of black cells that are surviving. And if I stick it in go forever mode and start running it like this, you can see you get these oscillating patterns. There's some sort of stable shapes like these arrangements of 4. There's other stable shapes like this. But over the other areas, you see these swirling patterns as they move between them. Eventually they seem to stabilize, but sometimes you get these oscillating patterns where they go backwards and forwards from one shape to another. And it goes on for quite some time. Most of the time when you set up with random initial conditions, it stabilizes to some particular shape, but you see there's still this kind of continual oscillation here. I'm going to let it run a bit and see what happens. One thing to note here while it's running all this time is that we have periodic boundary conditions. So cells on this side of the board interact with cells on this side of the board, the left and the right, and then the same with the top bottom. We often have these in these kind of complex system simulations, that we run everything on a donut, on a torus shape, so that we get an overall idea of what happens in the dynamics. It's better than having some sort of solid wall interaction. So this one's actually going on a lot longer than I usually have when I run this pattern. But I think I'll just let it go and you can watch it and we'll see if it eventually settles down. Now it's stuck in this oscillating pattern. Either you have a stable configuration like this, or you have a periodic configuration where it oscillates backwards and forwards.
One very nice pattern you find, or you're probably not going to find, but one nice pattern you can put in and test is something called the glider gun. The glider gun is shown here, and you'll see at the bottom there's this row of gliders coming out of this gun. And it keeps on producing these gliders one after the other, shuttling them round and producing them. Put in this pattern and you can see how it produces them. So one suggested way for classifying cellular automata as being class 4, this complex type of cellular automata, is the idea of universal computation. So a universal computing machine is a computer program that can simulate any other arbitrary computer program to produce the input that program, to produce the output that program would give. The main point really comes down to whether we can use a cellular automata to produce logic gates. With the two-dimensional game of life, we can actually use the glider guns to produce logic gates. They send the gliders to each other, they send on-off switches, and through that we could actually build up a computer. It would be a massive computer over a massive grid, but you could actually do it. The cellular automata, the game of life, can perform universal computing. Turns out that even simpler rules can produce universal computing. In fact, this rule 110, which I mentioned a few times, is exactly one of those rules. Now, I'm not going to go into the details of how Rule 110 works, but the way that it produces this universal computing builds up on the different patterns it can make. Here I show 3 of the different patterns it can make. It can make this line, it can make this sort of wiggly triangle, and it can make this stationary block of triangles. And how the logic gates work is basically to allow these triangles to crash into each other, or these structures to crash into each other and produce other shapes. And so you can get some idea of how that works in these pictures. You can have the wiggly triangles meet the line, and they produce a line and some more wiggly triangles. Or you can have the wiggly triangles meet a line and they produce the stationary triangles. And through these interactions, you can produce logic gates, and that can then be used to build up this universal computer. Of course, the complexity of the initial conditions to do any computation is massive. It's not as easy as switching on your own computer, that's for sure. Later on, we'll look at other ways which we can use to classify cellular automata and other types of complex systems in certain ways. One of them is self-similarity and box count and dimension. That's very useful for these Rule 90 type patterns where you get self-similarity. Another is entropy and complexity, which measure how varied a pattern is. And another one is Lyapunov exponent, and that measures how fast initial conditions are lost. So we'll come back to these measures in future lectures. Cellular automata were kind of the first models where people wanted to look at how simple interactions could produce complex patterns. They had some reasonable success with applications here, or at least they managed to reproduce patterns that's seen in nature. So I already mentioned in the first lecture the seashell example, and I give that here. And there's also examples where you can produce patterns like the BZ reaction using a cellular automata. You can also produce things like zebra stripes and leopard spots using simple cellular automata rules. There was a whole body of work on something called L systems, which allow you to make plant-like structures using simple cellular automata rules. Although there was a lot of early success in making cellular automatas that produce particular patterns, this hasn't really taken off as a scientific activity. They're more inspiration to the idea that simple interactions can produce complex patterns, rather than a real toolbox for scientific understanding. As such, we should really see cellular automata as a starting point, as an inspiration for looking at complex systems, rather than an end in themselves.